Okay, so in this particular video, I'll show you how to attack a straightforward velocity versus time graph. So if you want, read the scenario. It's kind of gibberish. There's a scenario if you want to read it. So I'll show you how to do A, B, C, D, E, F, and G. So we're given a velocity versus time graph here. And as you can see, to me, it's kind of nice. It's just a straight diagonal slope going upward. So the first thing to kind of notice here is that the object starts moving leftward. I know that because at times equal to 0, the slope of the graph intersects at -4, which suggests that the object is initially moving leftward. And then the other thing to point out is that it crosses the horizontal axis, which is your time, at 4 seconds. So right here at 4 seconds, I know it came to a stop. And then after 4 seconds, it moves in the forward direction. Why? Because everything else after 4 seconds is positive velocity. I know that because it is above the t-axis. Okay. All right. So let's go ahead and attack part A and B here on the slide. So part A asks us to find the dog's velocity at 2.5 seconds. So essentially, it just wants us to find the instantaneous velocity. So VF, we know our VF functions from our kinematics is A times delta t plus VI. So we can just go ahead and plug and chug. We know our delta t here is 2.5 seconds. I've chosen to go from 0 to 2.5. So that's, I think, is the easiest to do. The graph gives you your initial velocity at times equal to 0 is -4, and I'm just trying to go to 2.5. Okay, so therefore I can just plug in times 2.5. My VI here, I've used parentheses to indicate that VI itself is -4 meters per second. But you notice here I don't know what A is, so A is kind of holding me back from finishing out this particular part A, but that's easy to find. By now you should know that the velocity versus time graph, or the slope of a velocity versus time graph, this red diagonal line here, is your acceleration, because acceleration is change in v over change in time. So therefore rise over run, and that rise over run is our slope. So the slope of this red line is your acceleration. Okay, so let's go ahead and find A. We can find A by simply doing delta V over delta T. We can break up VF minus VI over change in time. At this particular point, it's up to you which two points on the line you want to use. I'm just going to go ahead and use the point here at the start, which is at times equal to 0. At times equal to 0, my initial velocity is -4, because that's where it crosses the vertical axis. That's your y-intercept. And then I've chosen to go all the way to 4 seconds, because at 4 seconds I know it came to a stop, because at 4 seconds the line crosses at a perfect diagonal there, and if I go all the way to the left of the graph, that puts me right at 0. So I know at 4 seconds it came to a stop, so I'll use those points just because it's easy to do. So here I plug in VF is equal to 0, minus comes from the function, and then again I'll use parentheses. It's important that you use parentheses, this way your negative signs doesn't mess with your outcomes later. VI itself is a negative value of 4 meters per second, but you notice here you have a negative sign in front, you have a negative velocity to start, so negative times a negative makes a positive, so it'd be 4 divided by 4, which is a positive 1 meters per second squared. And it also makes sense because to me this red diagonal is a positive slope. Again, in math, to find whether a slope is positive or negative, we go from left to right. So if you go from left to right, the slope is trending upward, so therefore the slope is positive, which is consistent with what I just found. Okay, so the acceleration in this case is 1 meters per second square. Now that we know what A is, we can just plug it in. Pretty easy work. All right, so VF we just carry down. So wherever A is, I plug in 1 meters per second square. I just carry the 2.5 seconds down, and then the initial velocity again is -4 meters per second. So here 1 times 2.5 is 2.5 plus a -4 will give you a value of -1.5 meters per second. Now you should check to see if the answer makes sense. So this tells me that at about 2.5 seconds that the velocity is -1.5. So on the graph I'll go over here, so this is 2, and 2.5 is where my cursor is kind of going back and forth here. If at 2.5 I'll go down to where it meets the line itself, the slope, and if I go all the way to the left, you know, that makes sense, as about -1.5, so I know my answer is reasonable. Okay, you should definitely check to make sure your answer is reasonable, just in case your science is off during your algebraic steps. All right, so that is my answer. And in this case, I don't need to include a direction because the direction is already indicated via the negative sign. So the negative sign tells you that it's moving leftward at a rate of 1.5 meters per second. All right, let's do part B. To do part B, we will just use the same strategy here. Vf is equal to A times T plus Vi, except this case, I'll use delta T as 6 because I want to go from 0 to 6. It's up to you. There's a different bunch of points you can choose, but I'll just use from 0 seconds to 6 seconds. If that's the case, we just found A in the previous part, which is 1 meters per second squared. Again, I'm going to go from 0 seconds to 6 seconds, so therefore my delta T is 6 seconds, plus my initial velocity. My initial velocity here, because at 0 second is -4, that's what I've chosen, so I'm going to go ahead and keep that as is. And if you simplify this, 1 times 6 is 6. 6 plus -4 will yield a +2. And the answer is 2 meters per second east, or you can use a plus sign in front. It doesn't really matter. Okay. All right, so there's that. If you want, you can check to make sure your work is right. At 6 seconds, when my cursor on the graph is going back and forth, if I go up to the graph, it meets the red line at that particular intersection there. But if I go all the way left, this value here where my cursor is tracing back and forth, that would be a 2, which makes sense because the interval here is 1, 2, and 3. So it does make sense that the answer is a +2. So I'm just going to move on. All right, part C. Part C asks you to find the total distance covered from 0 to 7 seconds for the entire time shown here in the graph. So the graph starts at 0 seconds and it stops at 7 seconds. It asks us to find the total distance. So the first thing I'd like to point out is that looking at this graph, you should recognize that it came to a stop. Okay, it came to a stop because the slope itself crosses the horizontal axis. Anytime it does that for a velocity time graph, you know it came to a stop. If it came to a stop, in this case, it started off heading in the negative direction. It came to a stop, and all of a sudden, all the velocity values after that is above the t-axis, which indicate that it's positive. So that tells me that the object, animal, person, whatever it is, changes direction. So in this case, the scenario has to do with the dog. So the dog kind of ran backward or ran leftward, and then kind of maybe saw whatever it is, stop, and then change direction and start chasing the whatever it is chasing to the right. So that's important to know. Okay. So therefore, here's the visual. So the dog is going to initially run leftward, and then it's going to slow down. So the arrows keep getting smaller, and then it's going to come to a stop, and then it changes direction. So it's going to come back in the opposite direction. Okay. So this is important because first, it moves leftward, and then it moves rightward. So to find the total distance, we have to find the total distance that it traveled leftward, and then we have to add the distance that it traveled rightward. So I'm going to break this into a couple of steps. All right, here, my first step is going to be from 0 to 4. I'm going to find the distance from 0 to 4 because that's where it changes direction. Therefore, to find the distance in this case, I'm just going to use my displacement function. I can use this per segment. So delta x here I can use just to find the distance going leftward. I cannot use it to find distance for the whole entire thing. Okay, so I'm going to go from 0 to 4 seconds because I know the dog is running leftward during that time interval. If that's the case, my VI is going to be -4, my time is going to be 4 seconds, A we found is 1, and then T here is going to be 4 seconds, and then the square is part of the function. So if you simplify all of this, you get -16 plus 8, and then therefore that's going to leave us with an answer of -8. So during the first 4 seconds, the dog ran a distance of 8 meters, but it's towards the left. So the absolute value here of your displacement, which is just 8, gives you the distance. So the distance during the first 4 segments is just 8 meters. Okay, even though I solve for displacement, I don't really care for the direction because this particular part just asks for distance. So just do the absolute value. So it ran 8 meters to the left. Okay, so that's the distance of 8. All right, let's do segment 2. For part 2, I'm going to take it from 4 seconds to 7 seconds. Here in this case, if you understand these arrows on the bottom of the screen, the dog came to a stop, changed its direction, and started running in the forward direction for 3 seconds. From 4 to 7 is 3 seconds. Therefore, I can use the same kinematics equation, except in this case, my VI is going to be 0 because at 4 seconds, your velocity is 4. Your velocity is 0 because it intersects at the horizontal axis here, okay? So therefore, the dog came to a stop. On the way back, the dog's initial velocity is 0 because it starts at 0, and therefore, really, it's just an easy plug and chug. It'd be 1/2 at squared, a being 1, t being 3, because from 4 to 7 is 3 seconds. You simplify that in your calculator, you should get 4.5 meters. Now, the question asks for distance during 0 to 7. Well, that's easy. It ran 8 meters during the first 4 seconds, and then it ran 4.5 meters during 4 to 7 seconds. So all we have to do is add that up, 8 plus 4.5, so the distance is 12.5, okay? To do distance, you don't need to include any sort of signs. Distance is a scalar, so 8 plus 4.5 is 12.5 meters. So that's your answer for part C. All right, now the other way to do it, is to find the area underneath a velocity versus time graph. So this triangle that just came up here is your delta x. So it's easy to find delta x because delta x is the area beneath a velocity versus time graph. So here my triangle is starting from 0 second and going to 4 seconds. Well, to find that area, which is a right triangle, I can just do 1/2 times base times height. Well, what's my base? You can go from 0 to 4. Okay, so here you just have to count carefully, and my height would be 1, 2, 3, 4 as well. So 1/2 times 4, and that'll give you a value of -8. This area is -8 because it's displacement, and displacement is a vector, so it needs a direction. But what's the distance? 8. Okay, so while the delta x here tells you that it's -8, to find the distance, you just do the absolute value, which is just 8. You can also use the same strategy for 4 to 7 seconds. Well, during 4 to 7 seconds, we know the dog ran to the right. So if you look at the shaded triangle that just came up, it's above the t-axis, which implies that delta x here is positive. Well, to find that area, we can just do the same thing. It's a perfect, right triangle, so 1/2 times base times height, and our base here is just 3, because from 4 to 7 is 3, and then if we count 1, 2, 3 in the vertical axis there, so 1/2 times 3 is 4.5, so delta x here is a positive 4.5, delta x here is -8, but to find distance, we simply just add this total shaded area without the negative sign, so it would be 8 plus 4.5, which gives us 12.5, okay? I like doing areas as long as you can count carefully and not mess up and make sure you shade properly. All right, let's do part D. Part D asks you to find the average speed during 0 to 7. Well, that's easy. We already found the total distance in part C for 0 to 7 seconds. So to find average speed, it's just distance over time, okay? And distance here is just 8 to the left plus 4 to the right, 4.5 to the right. So that'd be 12.5 divided by 7. So the answer is going to be 1.8 meters per second. And average speed is a scalar, so I don't need to include direction for that. So I'm done with that part. Part E asks us to find the average velocity from 0 to 7. Well, to do average velocity, you just have to, write these functions out. Average velocity, by definition, is the displacement divided by time. Okay, so your change in position over a change in time. Well, what's your displacement? Well, displacement is a vector. As I discussed earlier, the area here that we found, by shading or by doing math earlier, is -8. Where I'm going back and forth, that's -8. Well, this area that's above the t-axis is 4.5. But displacement is a vector, so when you do displacement, you have to account for the fact that the shaded area is beneath the t-axis, so therefore it's negative. So here, I've chosen to go -8 because the dog ran leftward for a displacement of -8. But then it turned around and ran forward for a displacement of 4.5. So by the end of the 7 seconds, the dog is only displaced 3.5 meters to the left from where it started. Okay, so therefore my displacement here is -3.5, and then I'm going to divide that by the total change in time, which is 7 seconds in this case. So the average velocity here for the dog during these 7 seconds is going to be -0.5 meters per second. That's my answer. The negative sign is your direction, so you don't need to put west or anything like that. Okay, so the direction is already included in this particular strategy. All right, so that's part E. Now, if you don't like doing displacement over time, you can also use this average velocity function here. I noticed that the slope of the red line that was given to me is a constant a, which is a positive 1 meters per second square. So therefore, I know I can find average velocity simply by taking vf plus vi divided by 2. Well, what's my vf and what's my vi? Well, that's easy to do. Oh, sorry, that came up twice. My vf here would just be 3. So at 7 seconds, if you take your pen to the graph here, at 7 seconds, you go up and you go leftward, and that meets it at 3 seconds. And then what's my initial velocity? My initial velocity at 0 second is -4, because that's where it intersects the vertical axis there. That's your y-intercept. So y-intercept here is just -4. So therefore, 3 plus -1, 3 plus -4 is -1, and then -1 divided by 2 will give you -0.5 meters per second as well. So you see the answer is very consistent. Okay, so that's that. Part F. Part F asks us to find the average velocity from 2 to 6 though, which is fine, right? 2 to 6 is not bad. Okay, so finding your displacement from 2 to 6, I know that the object is moving at a rate of -2 meters per second at 2 seconds. So all you have to do is go over the graph at 2 seconds. This graph is pretty nice. Right? There's no trick traps to this. At 2 seconds, you go all the way down to the red line, and then you go all the way across. And where my cursor is, that would be a value of -2. So this problem here starts at 2 and it ends at 6 seconds. So make sure you don't cross VI out. Okay, so VI in this case starts at 2 seconds. The graph indicates that at 2 seconds, it is moving at a rate of -2 meters per second. Well, what's your change in time? Well, change in time is 4, because from 2 to 6 is a difference of 4 seconds. A, we already calculated way back in part A, and here the time is 4 seconds as well. If you do all your calculator work, you should get a value of -8 meters for the first term here, plus 8 meters for the second term. So you have -8 plus 8. That will sum up to give you 0. Okay, which makes sense to me. Okay, so therefore your average velocity here is just going to be 0, because delta x in the numerator is 0, and then 4 seconds on the bottom, but who cares? 0 divided by 4 is just 0. So that's your answer. Now, let's check with the concept of shading areas. Well, in this particular case, it wants us to go from 2 to 6. So I can shade the area from 2 to 4 seconds, which makes a nice right triangle. And if it's a nice right triangle, then you can use 1/2 base times height. In this case, our base is going to be 2, because from 2 to 4 is 2. And then if you trace down from 0 all the way down to here, that is also 2. So 1/2 times 2 times 2 is -2. It's negative because this area is beneath the horizontal axis. Now we can use the same concept here. Well, we already shaded from 2 to 4 seconds. The next area that we need to shade is from 4 to 6 seconds, because that's what this time bound wants from us. Okay, so by symmetry, the area here in the top will also be 2. So if you want, you can count from 4 to 6, the base is 2. And if you count up 1, 2, and then you go to the left, that is a velocity of 2. So therefore 1/2 times 2 times 2 gives us 2, which makes sense. This shaded area here beneath the horizontal axis is -2. The shaded area is +2. So if you sum them up, the displacement would just be 0, because -2 plus 2 is 0, which makes sense. Okay, so if you want, you can use that strategy. If not, you can also use this strategy again, because A is constant. You can do V average is equal to VF plus VI divided by 2. Well, my VF is at 6 seconds. So at 6 seconds, if you trace on the graph, you go across, the velocity is a +2 because it's above the horizontal axis. So that's a +2. But then at 2 seconds, as I stated earlier, at 2 seconds, if you take your cursor and you go all the way down and you go to the left, this value here is -2. Well, VF is 2, VI is -2. 2 plus -2 is just 0. 0 divided by 2 will just give you 0, which is consistent with what we just calculated using the other kinematics equation. All right, let's do part G. Part G, this one, a little harder to do. It asks us to find the average velocity between 1.2 seconds to 3.7. So you notice here the times aren't exactly nice. It doesn't intersect the graph nicely. Okay, so let's do it. Average velocity by definition is delta x over delta t. I can find delta x easily. VIT plus 1/2 AT squared. Here, I know what t is. T is 2.5 seconds because the difference from 1.2 to 3.7 is 2.5 seconds. A, I know, so T I already know. The only thing holding me back here is VI. This particular problem starts at 1.2 seconds, but I don't know how fast it is moving at 1.2 seconds. And you cannot just kind of eyeball it, okay? You can see if your answer is right, but you can't just from the graph look at it and know what it is. So 1.2 seconds is where my cursor is tracing about here, right? If you go down, it touches the red line there, so I know it's a little less than -3 meters per second, but let's go ahead and find it. We can find it easy by by using the final velocity equation. Final velocity is equal to a delta t plus vi. But here I'm going to go from 0 to 1.2 seconds. Why? I know how fast it's moving at 0 second. At 0 second, it's moving at a rate of -4, and it's slowing down, so I can find how fast it's moving at 1.2 seconds. And that velocity will be my initial for the rest of the problem here. Okay, so here I plug in a is 1, I plug in delta t is 1.2 because I'm starting this particular part from 0 second going to 1.2 seconds because I can find how fast my velocity is at that moment in time. Well, if I start at 0 second, my initial velocity is -4 from the graph. So if I do this, I get a value of -2.8 meters per second. So if I, again, go back to the graph, I got to make sure my number is reasonable. 1.2 seconds, it's about here. I'm going to go down, touch the red line. I go all the way left, and the answer is 2.8, which makes sense. Okay, it's reasonable, right? So it's -2.8, so I'm just going to use that. Okay, I'm going to check, and my answer is reasonable, so I'm just going to move on. Therefore, I'm just going to carry this displacement function down, but where VI is, I'm going to plug in -2.8. And that's it, because 2.8 VI was the only thing that was missing in that statement. Okay, so I'm just going to find delta x, and if you do all this calculator work, you should get a displacement of -3.875 meters. And it's negative because at 3.7 seconds, it hasn't quite stopped yet. So all the area that's shaded will be beneath the t-axis, so the answer will be negative, which makes sense. So my delta x is -3.875. I want to plug that in for delta x. I'm going to carry this down, and then therefore average velocity here is -3.875 meters divided by 2.5 seconds, which is -1.6 meters per second. Okay, so that's my answer for this particular part. The negative sign again is your direction. I do want to point out though, it's difficult to shade for this one because at the time interval given is 1.2 to 3.7, so it didn't quite go to 4. So if you actually try to shade it, it is not a perfect right triangle. Okay, you can get an approximate, but you cannot use the shading strategy here because it is not a perfect right triangle. So I want to point that out. So you cannot use 1/2 times base times height. If you want to do that, it'll give you an answer close enough, but it won't give you an answer exact, okay? So I want to point out when to shade, when not to shade. 3.7 ends right about here. Well, right about there, you see this little white gap that I left open on purpose? That white, I don't know what that area is, because I don't know what that white area is. It makes this triangle that I have here not a perfect right triangle. Like it's kind of cut off a little bit, so it's not a really, well, technically it's not a triangle because this line here is not a sharp point. So if you need to, draw it out for yourself and kind of see what I'm talking about. Okay, so you don't get a right triangle. Because you don't get a right triangle, you cannot use 1/2 times base times height. Therefore, you have to use calculus to find the area. All right. So if you're in a calculus-based class, you can use calculus. Here, we know our velocity function. Your velocity function is given by this line. Okay, so therefore, we can just write y equals mx plus b. Y equals mx plus b is your velocity function. Here, your slope is just a +1 because we already found that. Or if you want, you can go 1 over 1 up. So 1 over 1 is 1, so the slope here is 1. And that's your acceleration. Your independent variable here is t. And then your y-intercept, for y equals mx plus b, your y-intercept is -4. So that's where this function comes from. Or really, it's just vf equals at plus vi, which is y equals mx plus b. Here, 1 times t is just t, and then plus -4, that's just -4. So if you know your velocity function, you can integrate your velocity function to find your displacement, or to find your x and t. Okay, so therefore here I've chosen to integrate v of t with respect to t. So to find x of t, you integrate your velocity function, and your velocity function here is just t minus 4. So here's t minus 4 with respect to t, and your time bound is 1.2 to 3.7 as indicated in the statement. To integrate this properly, integrating t would just give you t squared divided by 2, and then of the negative 4 would just simply turn into negative 4t plus c. And this is your coefficient, your xi, but the problem didn't give me the dog's initial position, so I'm just going to ignore it. I'm just going to cross it out. I'm going to treat it as 0 unless one is dictated for you. You can, or you need to run the test. Here it doesn't really matter, because if I plug this value in at times equal to 0, xi is just equal to 0. Okay. All right. So therefore, here's my bound. This is 1.2 to 3.7. So if you plug the values in for time, here you do the upper bound, subtract the lower bound. So wherever t is, you plug in 3.7. We're gonna square that, and then minus 4, and then the t is 3.7, and you do the same for the lower bound. So if you crank all your calculator work correctly, hopefully I didn't mess up here. But if you do all that, you should get this negative 7.99 minus a negative 4.08. And if you simplify that on your calculator, a negative here and a negative makes a positive. So really it's negative 7.995 plus 4.08, which gives you a value of negative 3.915 meters. Okay. And then to find average velocity, we can just do displacement, which is delta x here, divided by time. And then that will give us a value of negative 1.6 meters as well. All right. I hope that helps. Stay nerdy. Don't be whack.